Hi, I'm Wasu. In this video, I will be showcasing my project for big data, which involves keyword segmentation of retail products that are sold at Makro. Using k-means clustering, I will be defining the different segments and interpreting their meanings, as well as looking at how much sales they generate for Makro. First, let's take a brief look at the background of the project. For the problem statement, it's simple. Which segments of products drive sales in Makro? Yet, while it's simple, it requires multiple steps to come to a result, which may even turn out to be inconclusive depending on the process involved. These are the objectives that I've set for this project. First, obtain the data from Makro. Next, using this data, I will train a model to identify the different product segments. Finally, by looking closer into each segment, I can find out which segment drives sales. Here is a brief overview of the details involved for this project. For the number of features directly from the source project, I've kept it simple and limited at 2 features. This, however, is not to be overlooked as few. The reason for this is that the keywords can be further extracted into features later on. The model used is k-means clustering. Using this model alone without understanding is a bad idea. K-means is good if you want to measure distances between the different data points in order to identify the clusters that they belong to, and therefore numerical features would be needed. As such, all the features used would have to be in an appropriate type before being fed to the model. In order to do this, a pre-processing pipeline involving tokenization of the keywords and principal component analysis for the sake of dimensionality reduction will be used. Finally, the target is to obtain clear clusters within the limitations of the data provided, meaning the model should achieve a reasonably high silhouette score. Now, let's look at how the data was collected. This is Makro's new website for e-commerce called Makro Pro. In order to display products to the end user, it fetches data from its backend via API calls. To be precise, these API calls can be investigated by looking into the Network tab, by investigating the requests that are made alongside their respective responses. Certain requests are made to load the site skeleton, while others are used to collect telemetry in the form of cookies. The requests that I was interested in for this project involved those with JSON responses containing product data. Once I knew what these requests were, it was a simple matter of digging into their URL and mimicking the request body while changing its content to my desires. This would enable me to obtain different responses. There was one thing I noticed, however. The endpoints used involve something called GraphQL. As a fancy way of defining a standardized interface between the front end and the back end, GraphQL became a popular technology among web developers in querying data. Makro provided a GraphQL endpoint, which could be a data source. By looking closer into this endpoint via GraphQL Studio from Apollo, I could break down the components used for fetching products alongside understanding what the fields that a single product contained were. I set out to create a supergraph using Makro's endpoint and started digging into the fields. Using Apollo Studio, I created a GraphQL query based off of the information that I dug through. I was ready for the next step of making API calls using the query I wrote. While it sounds easy to obtain the data, there was an issue. The GraphQL endpoint needed the product ID for querying. In order to obtain this, I needed to get creative and find somewhere where Makro would list all of the product IDs. This left the search bar as an option for someone from the public. I investigated the network requests made when searching via the search bar, and I found that Makro provided a search API. I could add different filters to get different results. Aside from this, there was a maximum limit of results that I could get, so that I would have to paginate through the results iteratively. Finally, the API did not provide all of the product details for each product. I would still have to take the product ID from each product listed and query it using the GraphQL API, and finally merge it together to create a comprehensive list of products. To perform pagination, I had to guess the total number of pages, as this was not provided. Then, I would have to make a request to get the data for each page. To give you a glimpse of what that would look like, on the left is what a page looks like to the end user, and on the right is what the API returns. I set off to make my macro scraper for scraping data. First, I called the search API with a number of 145 that I obtained via trial and error. This would enable me to gather all the information of products and their IDs that the search API provided. I had to loop through the pages. Next, I queried the GraphQL API using the IDs that I obtained. However, the API would occasionally fail at times, and thus I needed a failsafe to prevent all the work from being lost. I thus split the process of querying the GraphQL API into different chunks with a mechanism to retry each chunk again after everything was over in the event of a failure. Finally, the post-processing process of the scraper would involve joining the results from the search API and the GraphQL API together again to obtain a comprehensive list of products. To give you a glimpse of how much data was gathered, around 20,000 products were gathered from around 100 Makro stores. Each item was so rich in details that their data contained deep nested fields, which had to be saved as a JSON file so that data was not lost or incorrectly parsed. After obtaining data via scraping, I was ready for analysis. First, the data itself was not clean. While it was nice not having to worry about the structure of the data since it was obtained from an API, the data contained features that weren't all useful, as well as some nested fields that are not for direct use, and also metadata that contained no meaning. To achieve the objectives set, I had to plan ahead. I find the underlying patterns in the products by loading the data first, then exploring and pre-processing it, and finally training a model and evaluating the said model to see if it is satisfactory for the usage. For loading, I utilized pandas to load the JSON data into a data frame. I then started by examining the rows involved to see what the data looked like and obtain an initial understanding. Next, I explored the data. This involved looking at the types, the values involved, the number of missing values, how the data was distributed, and the original schema. I also noticed that data scraped from the API contained tokenized versions of certain fields. Aside from being useful, these fields give an insight into the fact that Makro is preparing to perform analysis on the data as well. A little fun fact to learn about the company. Having noted these fields, I decided that keywords tokenized would be interesting to analyze, given that keywords play an important role in identifying products and optimizing their search engine optimization process. I then filtered out the necessary columns for analysis. Aside from eliminating the unused columns, this would help speed up the processes after, since only necessary data is retained and stored in memory. These fields include keywords, keywords tokenized, sold count for analyzing sales later, and title for labeling the points later. Next, I removed the null values from the data. I decided to go with removing the values directly since they were relatively few compared to the amount of data that was present. Any kind of imputation would be unnecessary in this case. Then, I cleaned the tokenized keywords. While Makro already had their keywords tokenized, I would still have to join them and strip out any unnecessary white spaces to make way for the next steps. I did not lower the characters to lowercase, as the tokenizer I would use would already perform this step. Then, this was stored in a new field. Now comes the interesting part. We cannot cluster using the tokens directly. To obtain a numerical representation of the tokens that is ordinal in nature, we would have to vectorize the keywords. This can be done using scikit-learn's TF-IDF vectorizer, which combines the term frequency for each term as well as the inverse document frequency. Term frequency measures the frequency of a term in a document. It is calculated as the number of times a term appears in a document divided by the number of times divided by the total number of terms in the document itself. TF is a local measure of a term's importance in a single document. Meanwhile, IDF, or inverse document frequency, measures the rarity of a term in a corpus. It is calculated as the logarithm of the total number of documents in a corpus divided by the number of documents that contain the term. IDF is a global measure of a term's importance across all documents in a corpus. TF-IDF is calculated by multiplying the term frequency by the inverse document frequency of a term. The resulting value is a measure of the importance of a term in a document relative to its importance in the corpus as a whole. We have now obtained a numerical representation for the keywords. Initially, when I mentioned the usage of only 2 features, I did not mention that I would obtain more from this process, which produces approximately 300 features. Prior to doing anything next, it is a good idea to convert the matrix to a data frame both for visualization and processing. While it looks cool, the massive number of features now pose an issue: extremely high dimensionality. To reduce this, I had to use PCA, or Principal Component Analysis, to reduce the dimensions down to an interpretable amount. I decided to go with 3 dimensions, which would be visually representable in a 3D plot. Each principal component gathers the most influential features together into themselves, enabling a reduced amount of dimensions to represent the same amount of information. Next is the training process. While data from the previous step is ready to be fed into a k-means model, the k, or the number of clusters involved, must be determined via a scoring system to obtain an optimal value. With a random k, the clusters may be inseparable and thus not the best fit for the data. To score each possible k value, we'll be using the silhouette score as a measure. Iterations run through k equals to 2 up to 14. A higher silhouette score indicates better defined clusters with greater separation between them. Via the elbow method, which iteratively goes through each k and calculates their silhouette score until no further improvements can be found, an elbow point at k equals to 4 was obtained. This means that 4 clusters would be optimal. Next, each point was labeled as falling into either one of the 4 clusters, depending on their distance to the closest cluster center. They are then visualized on the 3D scatter plot, which plots a different PCA component for each dimension. The visualization depicts clustering as shown, while also offering interactiveness as shown on the top right, so that the corresponding product title of each point can be viewed. So finally, what have I obtained from this model? Using the information from the k-means model, I was able to plot this graph of total sales volume within each cluster. This is plotted as a bar chart, which can be read as shown. Numbers on top of each bar represent the total amount of items sold for each respective cluster. An image of a sample product from each cluster is also shown. On the right, a smaller chart is shown representing the token frequencies of the top appearing tokens within each cluster. This is summarized to the top 3 tokens of each cluster on the bottom right. Now let's look at the insights obtained. First, Makro has 4 main segments of products when using keywords to segment them. These 4 main segments can be further broken down and analyzed. Second, the most popular segment, which is represented by the second cluster, has 7.1 million sold products. Unfortunately, however, no distinguishable characteristics can be found from examining products within this group or cluster. Finally, another interesting conclusion that can be found is that one entire segment of Makro's products are in-house Aero branded products. Such products make up around 7% of their sales volume. And using this information, Makro could increase the production of such in-house products even further to drive sales. With the conclusions over, let's look at the limitations of this research. So first, the dataset was limited to around 20,000 products with keywords that are possibly incorrectly labeled. For such a large amount of products, the input process of creating a new entry could leave room for error in a subjective field such as keywords. This could then lead to low-quality keywords that don't identify the products well, leading to misinterpretation of the data used. Next, for the tokenization process, the pre-generated tokens, while convenient, could be potentially incorrect. Aside from this, the usage of Thai and English keywords combined could be leading to issues in vectorization, wherein a single language alone would be better. Finally, there is a trade-off for the granularity of the tokens. Instead of representing a single word, a finer token would represent a syllable. And while this would be good for clustering, it would be hard to invert the results as shown and obtain meaning from each cluster. That will be it for the presentation. I would like to thank you for watching and hope you all have a nice day.